November 12, 1942, Richmond, California, Shipyard Number 2, 10:07 a.m. Pacific Wartime. The welding torches fall silent across ways number 3 as the final seam cools on hull SS Robert E. Peary. Henry Kaiser stands on the launching platform, his broad shoulders squared against the November wind coming off San Francisco Bay, watching 10,000 shipyard workers flood toward the ways. Photographers from Life magazine jostle for position. Navy brass stand rigid in their dress blues, faces carefully neutral. Behind Kaiser, the 441-foot cargo vessel sits complete, engine installed, deck equipment mounted, lifeboats secured, paint still wet on the hull numbers. 4 days and 15 hours and 29 minutes have passed since the keel touched these ways. Admiral Emery Land, head of the Maritime Commission, checks his pocket watch for the 3rd time in as many minutes. His jaw tightens. Traditional shipbuilding doctrine says a cargo vessel requires 230 days from keel to launch. The British Sunderland yards, with centuries of expertise, average 260 days. The revered Bath Iron Works in Maine needs 355 days for a destroyer. This man before him, this dam builder, this highway contractor, who has never designed a ship, never riveted a plate, never read a naval architecture text, has just shattered every assumption about marine construction that admirals have held since wooden ships ruled the seas. The champagne bottle swings, glass explodes against steel, SS Robert E. Peary slides backward down the greased ways, and somewhere in the Atlantic, another U-boat commander's mathematics have just become obsolete. Kaiser turns to the assembled dignitaries, that famous gap-toothed smile breaking across his face. "Gentlemen," he says, voice carrying over the crowd, "we've just proved that tradition is another word for yesterday's solutions." What nobody in that crowd knows, not the admirals, not the journalists, not even most of Kaiser's own managers, is that this 4-day ship represents just the visible peak of a revolution that has already rewritten American industrial capacity. In Kaiser's 7 West Coast shipyards, the mathematics of maritime warfare shift with each passing hour. While U-boats sink Allied merchant vessels at a rate of 1 every 4 hours, Kaiser's yards launch completed cargo ships faster than the Germans can torpedo them. The equation that Dönitz has built his entire Atlantic strategy upon, sink ships faster than America can replace them, has a fatal flaw. It assumes America builds ships the way nations have always built ships. Henry Kaiser has never read those assumptions. The story begins not in shipyards, but in desert construction sites and dam projects, in the mind of a man who solves problems by refusing to acknowledge they exist. Where traditionalists see the accumulated wisdom of centuries, Kaiser sees inefficiency waiting to be eliminated. Where naval architects see necessary complexity, he sees unnecessary steps. Where admirals see craftsmanship that cannot be rushed, he sees bottlenecks that can be removed. The collision between Kaiser's industrial philosophy and maritime tradition will produce more than ships. It will demonstrate that American manufacturing, properly organized, can overwhelm any opponent through sheer systematic efficiency. But first, the mathematics of disaster must become undeniable. January 1941. The North Atlantic, 300 miles southwest of Iceland. The SS Zeelandic breaks apart in 6 minutes. U-94's torpedo strikes the engine room at 03:42 hours, detonating 3,000 tons of aviation fuel bound for Britain. The blast wave travels through the hull at 18,000 feet per second, faster than the crew can process what's happening. Captain Lieutenant Herbert Kuppisch observes through his periscope as the bow section rises nearly vertical before sliding beneath the surface. No survivors. The entire event, detection, attack, sinking, departure, requires 11 minutes. Kuppisch's log notes: Americana Dampfer, 5,000 BRT, sunk with 1 torpedo. These merchant vessels possess no defensive capability and insufficient speed to evade. hunting conditions optimal. The mathematics appear inexorable. Germany's 91 operational U-boats in January 1941 sink an average of 3.2 ships per patrol. Each patrol lasts approximately 40 days. Total carrying capacity destroyed, 432,000 tons per month. Britain imports 68 million tons of supplies annually to survive: food, fuel, ammunition, raw materials, equipment. The island cannot produce sufficient resources domestically. Without the Atlantic convoy system, Britain starves and surrenders within 6 months. American and British shipyards respond with maximum effort. The established yards, Bethlehem Steel's Four River facility, Newport News Shipbuilding, Bath Iron Works, Harland and Wolff in Belfast, Swan Hunter on the Tyne, push production to unprecedented levels. Skilled riveters work 16-hour shifts. Naval architects expedite designs. Steel mills prioritize shipplate. Traditional shipbuilding methods, refined over centuries, operate at absolute capacity. The numbers tell a devastating story. British yards produce 1.2 million tons of new merchant shipping in 1941. American East Coast yards add 800,000 tons. Combined Allied production, 2 million tons. U-boat sinkings in 1941, 4.3 million tons. The differential, 2.3 million tons, represents the mathematical measure of Britain's approaching death. Each month, the merchant fleet shrinks. Each convoy arrives with fewer vessels. Each British civilian's ration decreases by calculated increments. At British Admiralty headquarters in London, analysts project the breaking point. Current trajectory indicates merchant fleet capacity will fall below survival minimum in March 1943. After that date, insufficient cargo capacity exists to maintain both the civilian population and military operations. Britain faces a choice between starving its people or abandoning the war. Churchill receives these projections in his underground war rooms and immediately requests expanded American shipbuilding. The Americans respond with a solution born from desperation and engineering pragmatism: the Emergency Shipbuilding Program. The Maritime Commission, established in 1936 to rebuild America's merchant fleet, receives unprecedented authority and funding. Admiral Emery Land, appointed chairman, faces an impossible mandate: build merchant ships faster than America has ever built anything, using a workforce that has never built ships, in yards that don't yet exist. Land's team designs the EC-2SC-1, emergency cargo vessel, second design, steam-powered, sea-level hull, first modification. Maritime historians will know it as the Liberty ship. The specifications emerge from pure pragmatism rather than elegance. Length, 441 feet, 6 inches. Beam, 56 feet, 10 inches. Depth, 37 feet, 4 inches. Displacement, 14,245 tons, fully loaded. Speed, 11 knots maximum, 8 knots cruising. The design copies a British tramp steamer from 1879, modernized with oil-fired boilers, but otherwise deliberately conservative. No innovations, no experimental systems. Nothing that can't be mass-produced by workers with minimal training. The engine represents Victorian technology wrapped in 20th century manufacturing. A triple expansion reciprocal steam engine, the same basic design that powered Titanic, generates 2,500 horsepower through 3 progressively larger cylinders. High-pressure steam, at 220 pounds per square inch, enters the first cylinder at 11.5 inches diameter, expands through a second cylinder at 22 inches, then exhausts through a third cylinder at 35 inches before condensing back to water. The system achieves merely 12% thermal efficiency, wasting 88% of its coal energy as waste heat. Modern turbine engines deliver 30% efficiency, but the reciprocating engine has one overwhelming advantage: any mechanic who has worked on a tractor or industrial pump can maintain it. Complexity kills production. Simplicity enables it. The Liberty ship design deliberately sacrifices performance for manufacturability. The hull uses straight lines rather than curves wherever possible, reducing the need for skilled plate bending. The bridge sits amidships rather than forward, allowing the bow section to be prefabricated as a simple pointed box. Deck equipment mounts on standardized bases with interchangeable parts. The entire vessel consists of approximately 250,000 individual pieces, each one designed to be made by different suppliers and assembled by semi-skilled workers following systematic procedures. Admiral Land distributes contracts to 18 existing shipyards specifying traditional riveted construction. Riveting represents 3,000 years of shipbuilding wisdom. Each rivet, a steel cylinder with a head on one end, passes through aligned holes in overlapping plates. A riveting crew of 4 men works with practiced precision. One heats the rivet in a portable forge to 1,900 degrees Fahrenheit, glowing cherry red. A second man catches it in a metal cup and places it through the aligned holes. A third positions a heavy steel dolly behind the existing head. A fourth swings a pneumatic hammer, deforming the protruding shaft into a second head that locks the plates together. Each rivet requires 45 seconds. A Liberty ship needs 500,000 rivets. The mathematics dictate minimum construction time, 10,400 man-hours just for riveting, assuming perfect efficiency and no mistakes. Skilled riveters serve 7-year apprenticeships learning their trade. They understand that rivets must be placed precisely. Too loose and the joint leaks, too tight and the plates crack under stress, too hot and the metal weakens, too cold and the rivet won't deform properly. The best riveters develop an intuitive sense for the work, hearing the change in hammer tone that indicates perfect compression. This expertise cannot be taught quickly. It cannot be systematized. It represents the accumulated knowledge that makes shipbuilding a craft, rather than merely an industry. The first Liberty ship keel lays on April 30th, 1941, at Bethlehem Fairfield Shipyard in Baltimore. SS Patrick Henry launches 244 days later on September 27th. President Roosevelt speaks at the ceremony, invoking Patrick Henry's Revolutionary War Declaration, "Give me liberty or give me death." The ship enters service in October, crossing the Atlantic with 10,800 tons of steel, tractors, locomotives, and crated aircraft. The Maritime Commission declares success. Traditional shipyards, using traditional methods, can build these simplified vessels in 240 days versus 355 for custom designs. It's not fast enough to outpace U-boat sinkings, but it demonstrates industrial mobilization is occurring. Then, Henry Kaiser's telegram arrives at Admiral Land's office. The message, dated August 1941, consists of 47 words. Can build ships faster, using West Coast methods. Stop. Request contract for 30 vessels. Stop. Will deliver in half-time of East Coast yards. Stop. Have no shipbuilding experience, but understand mass production. Stop. Respectfully, Kaiser Industries. Admiral Land reads the telegram 3 times. His initial response, preserved in Maritime Commission archives, consists of a single word scrawled across the top: absurd. But Britain continues dying in measured monthly increments. U-boat wolf packs savage convoys with increasing efficiency. Admiral Karl Dönitz perfects group tactics. Submarines spread in patrol lines across convoy routes, first boat to detect targets. Radios the position, entire pack converges for coordinated night surface attacks that overwhelm escorts. Convoy SC-42 loses 16 of 64 ships in 4 days. Convoy SC-52 loses 11. The mathematics inexorably point toward British collapse. Admiral Land reluctantly approves Kaiser's proposal, assigning 30 Liberty ships with one condition. Kaiser must partner with Todd Shipyards, an established builder with actual maritime expertise. The contract specifies 190-day delivery for the first vessel, declining to 110 days by the 30th. Land considers these targets optimistic for a newcomer. He has no framework for understanding what's about to occur. Henry Kaiser arrives in Richmond, California, with a conviction that will reshape industrial warfare. There is no such thing as shipbuilding tradition, only habit disguised as necessity. His background contains not a single maritime credential. Born in 1882 in Sprout Brook, New York, Kaiser leaves school at 13, works as a photographer's apprentice, then gravitates to construction. He builds roads in the Pacific Northwest, dams across the West, bridges over impossible canyons. His method remains consistent: ignore established practice, analyze the actual problem, design systematic solutions, and drive execution with relentless urgency. The Hoover Dam project showcases Kaiser's philosophy. Traditional approaches project a 12-year timeline. Kaiser's consortium completes it in 5 years through innovations that horrify conventional engineers. Pouring concrete in interlocking blocks rather than continuous layers, using embedded cooling pipes to prevent cracking. Employing around-the-clock shifts to maintain momentum. Treating every delay as a solvable logistics problem rather than an inevitable setback. Civil engineers declare it reckless. Kaiser delivers 2 years early and under budget. He approaches shipbuilding with identical assumptions. Nothing about the process is sacred. Everything is negotiable, and speed matters more than aesthetics. Kaiser walks the Richmond site in September 1941, observing Todd Shipyard's personnel laying out traditional construction procedures, building ways for keel-up assembly, installing riveting equipment, recruiting certified maritime tradesmen. He sees bottlenecks everywhere. The revolution begins with a material choice that makes admirals blanch. Kaiser abandons riveting entirely in favor of welding. Welding joins metal through fusion rather than mechanical fastening. An electric arc, jumping between a consumable electrode and the base metal, generates temperatures exceeding 6,500 degrees Fahrenheit, hot enough to melt steel. The electrode melts into the gap between plates, pooling as molten metal that solidifies into a continuous joint stronger than the original material. A skilled welder moves the electrode along the seam at controlled speed, maintaining precise arc length and electrode angle, creating a weld bead that fuses the plates into a single piece. The process requires weeks of training versus years for riveting. One welder replaces a 4-man riveting crew. A welded hull uses 600 tons less steel than a riveted one because overlapping plates aren't necessary. Welding time per joint, 90 seconds versus 45 seconds for a rivet, but the mathematics shift dramatically when counting total joints. A welded hull requires 15,000 welds instead of 500,000 rivets. Total labor time falls from 10,400 hours to 6,250 hours. Naval architects oppose welding based on legitimate structural concerns. Welded joints create internal stresses as molten metal cools and contracts. These residual stresses can propagate cracks under load, especially in cold water temperatures that make steel brittle. The Titanic's hull plates shattered rather than bending because the steel became brittle at freezing North Atlantic temperatures. Welded ships potentially face similar catastrophic failures. A crack starting at one weld might race through the entire hull like a zipper, splitting the vessel apart in minutes. Riveted joints, by contrast, contain failures. If one rivet fails, the crack stops at that joint rather than propagating. This represents centuries of maritime safety wisdom. Admirals reasonably question whether Kaiser's welding gamble will produce ships or floating coffins. Kaiser addresses these concerns through systematic engineering rather than theoretical debate. He recruits metallurgists from the construction industry who have welded bridges and dams under high-stress loads. They analyze the problem methodically. What causes weld failures? Stress concentrations at sharp corners. Solution: design hull sections with radius transitions rather than square corners. What makes cracks propagate? Continuous weld seams spanning entire sections. Solution: stagger welds and install crack arrest straps at regular intervals. What causes brittle fracture? Wrong steel alloy at low temperatures. Solution: specify steel with higher nickel content that maintains ductility at freezing temperatures. The Maritime Commission tests welded sections by deliberately creating stress cracks, then measuring how far they propagate. The results show that properly designed welded joints actually contain failures better than riveted construction. A crack in a welded hull with crack arrest features propagates an average of 12 feet before stopping. A crack in a riveted hull can separate an entire section as rivets pop sequentially. The testing validates Kaiser's approach, but Admiral Land remains skeptical. 3,000 years of maritime tradition don't overturn because some dam builder ran a few tests. Kaiser's second innovation attacks the fundamental paradigm of shipbuilding. He refuses to build ships on ways. Traditional construction assembles vessels from keel upward on angled launching rails. Workers swarm over the growing hull, installing plates and frames and equipment in sequence, each trade waiting for the previous trade to finish. Riveters follow behind platers. Pipe fitters follow riveters. Electricians follow pipe fitters. The process creates constant worker movement, endless coordination overhead, and brutal inefficiency. Workers spend more time climbing ladders and waiting for access than actually building. Kaiser reimagines the entire process around modular prefabrication. The ship breaks down into major subassemblies constructed separately: bow section, stern section, midship sections, deckhouse, engine room, cargo holds. Each module builds in a specialized prefabrication yard where all equipment, cranes, welding stations, material storage, positions optimally for that specific component. Workers don't move, components come to them. A bow section team fabricates 15 identical bow sections simultaneously in a dedicated building. A stern team does likewise. An engine room team pre-installs all machinery, piping, and wiring in the engine room module before it ever approaches the hull. The construction sequence transforms from linear to parallel. Instead of building one ship sequentially, Kaiser's yards build components for multiple ships simultaneously. 50 welders working on 50 different bow sections complete 50 bows in the time traditional methods build one complete ship. The mathematics of parallel processing overwhelm traditional sequential construction. The modules themselves showcase Kaiser's construction background. Each major section, bow, stern, midship, is further divided into standardized panels. A bow section consists of 44 individual panels, each small enough to be fabricated at a comfortable working height, then lifted by crane and welded into position. Workers never climb higher than 6 feet. No scaffolding required. No worker fatigue from awkward overhead welding. Each panel station becomes a specialized factory cell producing identical components with increasing efficiency as workers master the repetitive task. Kaiser installs his modular construction system at Richmond Shipyard No. 2 in November 1941. The facility sprawls across 140 acres of former marshland, specifically chosen for cheap land and deep water access. 7 parallel shipways run perpendicular to the bay. Behind them, massive prefabrication buildings, each one covering 5 acres, house the modular construction teams. Overhead cranes rated at 50 tons capacity travel on rails between the prefab buildings and the ways, moving completed modules. The entire yard is designed around one principle: minimize the time components spend on the ways. The workforce Kaiser recruits makes traditionalists shudder. Shipbuilding unions specify 7-year apprenticeships for journeyman certification. Kaiser has 7 weeks. He hires farmers from the Dust Bowl, housewives whose husbands are deployed overseas, African Americans fleeing Southern segregation, workers from failed industries, anyone willing to learn. The Richmond yards eventually employ 90,000 people, of whom perhaps 200 have prior shipbuilding experience. This violates every assumption about maritime craftsmanship. Kaiser's training program reflects his conviction that complexity is a choice, not a requirement. New welders attend a 2-week course focusing on a single task, making straight welds on flat plates in the overhead position. That's it. No artistry, no complex joints, no multipass techniques. Just one specific weld type, repeated until muscle memory takes over. After 2 weeks, trainees become production welders, fabricating hull panels. They do one thing, the same thing, thousands of times, building speed and consistency. Specialists handle the complex structural welds. Everyone else does simple, repetitive work that requires competence, not expertise. The same pattern applies to every trade. Electricians learn to pull cable through specific conduit configurations, not electrical theory. Pipe fitters learn to install pre-cut, pre-threaded sections following color-coded drawings, not engineering principles. Each worker masters a narrow task rather than learning the entire craft. Traditional tradesmen consider this degrading, reducing skilled craftsmanship to factory assembly. Kaiser considers it efficient. Charles Bedaux, the industrial efficiency consultant, visits Richmond in January 1942 and later writes, "Kaiser has done to shipbuilding what Ford did to automobiles. He's discovered that building one ship well requires highly trained craftsmen. Building 5,000 ships adequately requires systematic processes that allow ordinary people to do extraordinary work. The admirals see this as tragedy. I see it as the only way America survives." The first Kaiser Liberty ship, SS Ocean Vanguard, launches in April 1942 after 196 days of construction. Admiral Land considers this acceptable for a first effort but unremarkable compared to East Coast yards, now achieving 180-day builds as their workforce gains experience. Kaiser has proved he can build ships. He hasn't proved he can do it better than traditional methods. Then the learning curve begins. Kaiser's modular system improves with every vessel. The second ship requires 172 days. The fourth requires 149 days. The eighth requires 118 days. By June 1942, Richmond Shipyard No. 2 launches SS Robert E. Peary's Keel, and Kaiser announces a demonstration. This vessel will showcase the absolute minimum construction time possible. Every prefabrication team, every crane operator, every welder has practiced their specific role. The components are ready. The sequence is planned. 7 days earlier, yard managers conducted a complete dry run using wooden mock-ups, timing every movement, identifying every bottleneck. The operation begins at 12:01 a.m. on November 8, 1942. Keel sections lower onto way number 3. 2 massive beams running 441 feet, already containing the keelson plates and bottom framing. By dawn, the first midship section swings over the keel, positioned by crane operators who have moved identical modules 400 times before. Welders secure it, using pre-drilled holes with perfect alignment. No measuring, no adjusting. The components fit because the prefabrication jigs guarantee identical dimensions every time. Hour 15, bow section attaches. The massive 65-ton component contains all forward framing, anchor chains, collision bulkhead, crew quarters, and forward cargo hold, complete with lighting and ventilation. Workers inside made every electrical connection, installed every fixture, tested every system before the bow left the prefab building. It drops into position, and welders secure it with 237 predetermined welds. Total time to attach and secure, 4.5 hours. Hour 28, stern section attaches. This 80-ton module contains the entire propulsion system, engine, propeller shaft, rudder assembly, steering gear, all pre-installed and tested on a dummy foundation. The engine fired up and ran in the prefab building, pumping water through the cooling system, turning the shaft, verifying every bearing and seal. When it attaches to the hull, the propulsion system is already functional. Traditional shipbuilding installs the engine after launching, requiring months of alignment and adjustment. Kaiser's engine aligns perfectly because the mounting points were machined to tolerances of 0.005 inches during prefabrication. Hour 42. Midship deckhouse lowers onto the hull. This prefabricated structure contains the bridge, radio room, officer quarters, galley, mess hall, medical bay, everything above the main deck, complete with furniture, equipment and wiring. The crew could live in it immediately. It weighs 45 tons and positions in 37 minutes because guide pins on the bottom align with receptacles welded into the deck. No surveying, no adjustment. It fits because manufacturing tolerances guarantee it. Hour 67. Cargo booms and masts install. These massive steel structures, each boom capable of lifting 15 tons, arrive complete with rigging and mechanical systems. Traditional yards spend weeks installing and adjusting boom geometry to ensure proper lifting angles. Kaiser's booms install in 4 hours because every dimension was calculated during design and verified during prefabrication. The first time they lift a load is during final testing, and they work perfectly because they were built to work perfectly. Hour 89. Lifeboats mount on davits. 6 complete boats, provisioned with emergency supplies, swung into position by crane. Traditional yards mount empty boats, then load supplies. Kaiser's boats arrive ready for abandonment. The life raft canisters even contain water and rations. Nothing remains incomplete. Hour 101. Painting crews finish the hull. The paint itself represents systematic innovation. Kaiser's chemists developed a fast-drying formulation specifically for this project. Conventional marine paint requires 48 hours between coats. Kaiser's paint dries in 6 hours and achieves equivalent corrosion protection. The chemical innovation attracts no attention because it doesn't make for dramatic headlines, but it exemplifies Kaiser's philosophy. Everything is negotiable. Every constraint can be challenged. Every tradition can be replaced with something faster if you engineer the solution properly. Hour 112. Final systems testing. Electrical crews energize the entire ship, verifying every circuit, every motor, every pump. The engine fires, steam pressure builds, the propeller shaft rotates, steering gear cycles through full travel, anchor windlass drops and retrieves the anchor, cargo winches lift test loads, radio equipment transmits test signals. Every system operates exactly as designed because every system was tested in prefabrication, then tested again during installation, then tested once more as an integrated ship. The testing doesn't discover problems. It verifies absence of problems. Hour 115. Final inspection. Maritime Commission surveyors walk through the completed vessel with checklists, examining welds, verifying equipment installation, checking regulatory compliance. They find nothing wrong. The ship meets every specification. It's not beautiful. The welds show tooling marks. The paint has sags. The fittings lack the polished finish of traditionally crafted vessels. But it's complete and seaworthy. Hour 115 hours, 29 minutes. Launch clearance granted. November 12th, 1942. 10:07 a.m. SS. Robert E. Peary slides down the ways and floats free. 4 days, 15 hours, 29 minutes from keel to launch. The crowd erupts. Photographers capture the moment. Newsreel cameras roll. The impossible has occurred. Admiral Land delivers brief remarks that carefully avoid enthusiasm. This vessel demonstrates the capacity of American industry to mobilize effectively. It should not be assumed that such accelerated construction represents normal capability. Kaiser grins and tells reporters, "Normal capability is what you achieved yesterday. Today's achievement becomes tomorrow's normal." What Admiral Land doesn't say, what he perhaps doesn't fully comprehend yet, is that Robert E. Peary doesn't represent Kaiser's maximum capability. It represents a demonstration run, a proof of concept, a statement that the old rules are dead. Kaiser's 7 shipyards already operate on the assumption that every Liberty ship can build in under 30 days. Richmond Yard, number 2, launches 3 complete ships per week by November 1942, 3 complete ocean-going cargo vessels, every 7 days, forever. The mathematics destroy German naval strategy. Admiral Karl Dönitz's entire Atlantic campaign depends on a simple calculation. Sink ships faster than enemies can replace them. U-boats must destroy more than 2 million tons annually to outpace Allied production. Through November 1942, they succeed. U-boat fleet reaches 212 operational submarines. Sinking rates approach 600,000 tons monthly. Dönitz's staff projects victory by spring 1943. Then, Kaiser's production numbers reach German intelligence. The reports seem absurd. 1 yard producing 3 ships weekly. Impossible. German naval architects review the intelligence, assume transcription errors, reduce the estimates by 80%, and report that American production may reach 2 million tons annually if maximum mobilization sustained. Even this conservative estimate worries Dönitz. The actual numbers: Kaiser's 7 West Coast yards produce 1,490 Liberty ships between 1942 and 1945. Total tonnage: 20.8 million tons. Add the 18 East Coast yards that eventually adopt Kaiser's methods, and American Liberty ship production reaches 2,710 vessels, totaling 38 million tons. German U-boats sink 15 million tons of Allied shipping during the entire war. America replaces those losses 2.5 times over, but raw production numbers only tell part of the story. Kaiser's true revolution lies in the systematic dismantling of every assumption about what ships require. The engine room of SS Joseph N. Thiel, Kaiser Hull, number 440, illustrates this philosophy through painful simplicity. The engine represents obsolete technology even by 1890 standards, a massive triple expansion reciprocating design that Conrad's steamship captains would recognize. It burns 60 tons of bunker oil daily to maintain 11 knots. Modern turbine engines consume 40 tons for 15 knots. The Liberty ship's engine converts barely 12% of fuel energy to propulsion, wasting the rest as heat radiated through massive cooling systems. Naval architects initially protest this choice. Modern engines exist. Why install antiques? Kaiser's response addresses operational reality rather than engineering pride. The triple expansion engine has 0 exotic components. Every part can be manufactured by railway machine shops, tractor factories, or heavy equipment producers. No specialized metallurgy required. No precision turbine blades demanding aerospace-grade manufacturing. A crankshaft is a crankshaft. Whether it powers a locomotive or a ship makes no difference to the foundry casting it. Maintenance philosophy follows the same brutal pragmatism. Turbine engines require specialists. Triple expansion engines require a wrench and common sense. Any chief engineer who has maintained industrial equipment can rebuild a Liberty ship's power plant using standard hand tools. The instruction manual consists of 47 pages with detailed exploded view drawings. Compare this to contemporary destroyer turbine manuals running 600 pages of complex procedures requiring factory training. The strategic calculation becomes obvious. One complex ship immobilized in port for repairs contributes 0 to winning the war. 10 simple ships, 9 of which remain operational while 1 undergoes maintenance, deliver 90% of their theoretical capacity. The engineering elegance that makes naval architects proud becomes a strategic liability when deployed at scale. Kaiser understands this intuitively. His dams use simple concrete construction rather than innovative arch designs because simple scales better than clever. Every system aboard Liberty ships reflects this philosophy. The steering gear uses hydraulic rams directly connected to the rudder stock, no complex gearing or electric motors. Cargo booms operate through simple mechanical advantage with steam winches providing power. Electrical systems run on 120 volts DC because every small-town electrical shop can repair DC generators. Radio equipment uses vacuum tubes in standard sockets rather than custom components. Even the galley stoves burn the same bunker oil as the main engine, eliminating need for separate fuel systems. Robert Wilson, chief engineer aboard SS John W. Brown for 32 Atlantic crossings, later explained, "Naval officers hated Liberty ships because they weren't elegant. We loved them because they worked. The engine room had no mystery. If something broke, you fixed it with tools you already had. I once rebuilt the feed water pump in the middle of the North Atlantic using spare parts cannibalized from the bilge pump. Try that on a destroyer. The Liberty ship was a truck that floated. Basic, reliable, repairable by anyone with mechanical sense. This repairability becomes combat critical when enemy action damages ships." SS Richard Montgomery takes a torpedo from U-270 that floods the forward cargo hold and damages the bow structure. Traditional vessels would require dry dock repairs. Montgomery's crew shores up the bulkhead using timber, pumps the hold, and continues to port under power. The modular construction means damage remains contained. The simple systems mean improvised repairs work. The ship survives to deliver its cargo. The Liberty ship's structural design deliberately trades optimal performance for damage tolerance. The hull uses heavier steel than necessary. 26-pound plate where 22-pound would suffice by calculation. This adds 400 tons of unnecessary weight, reducing cargo capacity and wasting steel. But it provides safety margin against both combat damage and inevitable construction flaws when built by workers with 6 weeks training. Every weld doesn't need to be perfect when the structure includes 15% excess strength. Traditional naval architecture seeks efficiency through minimal materials. Kaiser's architecture seeks survivability through redundancy. The parallel construction process also generates unexpected quality advantages. When Richmond Yard No. 2 builds 50 identical bow sections simultaneously, any design flaw immediately manifests 50 times. This forces instant correction rather than allowing problems to propagate through serial production. Traditional yards might build 30 ships with a subtle engine mounting misalignment before someone notices. Kaiser's yards discover the same problem. When the first module fails testing, fix it in the templates and never repeat it. Quality control itself becomes systematized. Each prefabricated module passes through 5 inspection stations before installation. First inspection, dimensional verification using go-no-go gauges. Second, visual weld inspection by certified inspectors examining every inch. Third, ultrasonic testing of critical structural welds. Fourth, hydrostatic testing of all tanks and piping systems. Fifth, functional testing of all installed equipment. Only modules passing all 5 inspections proceed to the ways. This screening means final assembly rarely encounters defective components. The statistical results demonstrate the effectiveness. Kaiser ships average 1.2 defects per 1,000 welds discovered during maritime commission acceptance testing. East Coast yards using traditional methods average 3.7 defects per 1,000. Kaiser's systematic approach, using workers with minimal training, produces fewer defects than traditional craftsmen because the process eliminates opportunity for error. When every weld location is precisely specified, every electrode type is specified, every current setting is specified, and every inspector checks every joint, individual skill matters less than systematic compliance. But even perfect construction means nothing if ships don't reach the battle. The Kaiser yards create an integrated production to deployment system that treats shipbuilding as logistics problem. Traditional shipyards deliver completed vessels to the Navy, which then schedules shakedown cruises, training periods, and eventual deployment across months. Kaiser's ships proceed from launch directly to loading dock, The crew joins during final construction, learning the vessel while it's built. By launch day, the engineers know every pipe valve, electricians know every junction box, deck crew knows every winch and boom. No learning curve after delivery. The crew trained on their specific ship during its assembly. Loading begins before the paint dries. While the ship sits at the fitting out dock, completing final systems checks, cargo begins arriving. Liberty ships can carry 10,800 tons, distributed across 5 cargo holds. The loading plan, which cargo goes where, is calculated during construction based on the vessel's first mission. Cargo manifests arrive from the Warshipping Administration, specifying exact loads. 200 tons of ammunition in Hold 1, 2,000 tons of steel plate in Hold 2, 150 Sherman tanks secured on deck, 500 tons of aircraft parts in Hold 3, 3,000 tons of flour, and canned goods in Holds 4 and 5, 45 locomotives as deck cargo. The loading choreography requires precision logistics. Heavy items load first, low in the hull for stability. Ammunition loads in specially ventilated holds with spark-proof fittings. Deck cargo, tanks, locomotives, aircraft, vehicles, chains down using designated mounting points built into the deck structure. The entire loading operation completes in 36 hours using specialized cargo handling equipment that Kaiser designed specifically for Liberty ships. Forklifts move palletized cargo. Mobile cranes position heavy equipment. Conveyor systems fill holds with bulk goods. One ship loads faster than traditional methods could empty it. 7 days after launch, SS Robert E. Peary departs San Francisco carrying full war cargo, plus 30 tons of fresh vegetables and frozen beef. Destination: Townsville, Australia. The vessel that didn't exist 9 days earlier now contributes directly to Pacific combat operations. This integration, construction, testing, loading, deployment, without traditional delays, means Kaiser ships reach combat service weeks faster than conventionally built vessels. The production advantage compounds into a deployment advantage. The strategic impact manifests in brutal arithmetic. U-boat campaign reaches peak effectiveness in March 1943. 108 Allied merchant ships sunk totaling 627,000 tons. But Allied production that month: 219 new merchant vessels totaling 1.3 million tons. Dönitz's Wolfpacks sink 627,000 tons. America builds 900,000 tons just from Liberty ships alone, before counting other vessel types. The Germans fight a mathematical battle that was lost before it began. German intelligence finally grasps the scale of American production in May 1943, when decoded transmissions reference specific Kaiser ship names. U-boat commanders report attacking vessels with only 2-digit hull numbers, indicating extreme production volumes. Commander Heinrich Schroeder's patrol log notes: torpedoed American freighter William G. Lee, marked hull 47. Either American numbering system differs from European conventions, or they have built 47 identical vessels. If the latter, our strategic assumptions require immediate revision. They had built 447. By May 1943, Kaiser alone delivered more tonnage than the entire German merchant marine contained before the war. Admiral Dönitz realizes the campaign cannot succeed and recommends withdrawing U-boats from the Atlantic to cut losses. Hitler refuses, insisting the submarine fleet must tie down Allied anti-submarine forces even if the cargo war is lost. The strategic shift, from attempting victory to merely creating problems, acknowledges Kaiser's fundamental impact. Germany cannot win the Atlantic War because America's industrial response overwhelms German naval capacity. But Kaiser's methods face their own crisis when structural reality intrudes on production enthusiasm. January 16, 1943, Pacific Ocean, 700 miles west of Washington State. SS Schenectady, Kaiser Hull 1064, proceeds north toward Alaska, carrying Army cargo. Air temperature, 38 degrees Fahrenheit. Water temperature, 42 degrees. Moderate seas, no combat, no damage. At 01:55 hours, the deck watch hears a crack like artillery. The ship shudders. Emergency lights illuminate. The chief engineer, racing from his cabin, finds the impossible. The vessel has broken in half. The fracture runs completely across the main deck just aft of the bridge. The bow section droops downward, held to the stern only by bottom plates and keel. The crack extends 70 feet across the deck, through both side plates, severing everything above the waterline. The ship remains afloat only because bulkheads contain flooding and the bottom structure remains intact. An emergency weld crew joins the sections sufficiently to allow slow transit to port. Photographs of Schenectady being towed into Portland with the massive crack visible across its deck reach every newspaper. Admirals who opposed welding erupt with vindication. This validates every concern about welded construction. Welded joints create stress concentrations. Cold water makes steel brittle. Kaiser's rush to production sacrificed safety. The Maritime Commission launches an investigation. Liberty ship construction temporarily pauses pending review. Traditional shipbuilders publicly suggest returning to riveted construction exclusively. The investigation reveals complex metallurgical reality. Schenectady didn't fail because of welding. It failed because of steel chemistry. The original Liberty ship specification called for mild carbon steel, the same alloy used for bridges and buildings. This steel becomes brittle below 60 degrees Fahrenheit, transitioning from ductile behavior, bending under stress, to brittle behavior, fracturing under stress. The transition temperature was known to metallurgists, but wasn't considered critical for ships operating in temperate waters. The Pacific Campaign and Murmansk convoys exposed Liberty ships to sustained operation in near-freezing conditions. The steel, stressed by normal wave action, suddenly faced loads while in brittle state. Microscopic flaws, inclusions in the steel, slight dimensional mismatches at joints, stress concentrations at corners, became crack initiation sites. Once started, cracks propagated through brittle material like breaking glass. The welded construction didn't cause the failures. It just allowed rapid crack propagation that riveted construction would have arrested. The fix requires metallurgical adjustment rather than construction method changes. Maritime Commission specifies higher nickel steel alloys that maintain ductility at lower temperatures. Structural engineers add crack arrest features. Heavy steel straps welded across critical areas that stop crack propagation. Naval architects redesign high-stress areas, eliminating square corners and adding radius transitions. Every Liberty ship under construction receives these modifications. Every completed ship returns for retrofit installation of crack arrest straps. 3 Liberty ships suffer catastrophic structural failure during the war. SS John P. Gaines breaks in half in December 1943. SS Esso Manhattan fractures while loading in port. Each failure teaches specific lessons that feed back into design improvements. Traditional shipbuilding would have treated these as evidence that radical innovation was wrong. Kaiser treats them as data points, revealing which specific variables need adjustment. The difference in response philosophy, innovation stopped versus innovation refined, determines who wins industrial wars. The structural problems, while dramatic, affect fewer than 1% of Liberty ships. The remaining 99% complete their service without catastrophic failure. The 3 total losses to structural failure compare to 200 Liberty ships lost to enemy action and 300 to weather and collision. The welded construction, despite its publicized problems, proves more reliable than the marine environment. Beyond structural concerns, Kaiser faces legitimate criticism about habitability. Liberty ships are miserable places to live. The crew quarters, berthing for 44 merchant seamen, plus 21 naval armed guard, occupy cramped spaces in the bow and stern, areas with maximum motion in rough seas. Bunks stack 3 high with 24 inches of clearance. No air conditioning exists. Ventilation depends on wind scoops and small fans. The only fresh water comes from evaporators producing 1,500 gallons daily, barely sufficient for drinking, cooking, and minimal washing for 65 men. Showers operate on rationed schedules, 5 minutes per man, 3 times weekly. Toilet facilities serve 8 men per fixture. The galley equipment consists of coal-fired ranges that make the space brutally hot, regardless of external temperature. Compare this to passenger liners or even military transports that provided reasonable crew comfort. Liberty ships offered none. Merchant seamen called them floating coffins and ugly ducklings, terms that reflected both the structural failure concerns and the miserable living conditions. Crews tolerated these conditions because wartime service paid well and alternatives meant unemployment, but nobody considered liberty ships pleasant duty. William McCalmont, able seaman aboard SS Benjamin Conti for 5 Atlantic crossings, described conditions in his memoir. "You never got dry. The bow quarters leaked around the hatches every time seas ran heavy. Condensation dripped from the steel overhead constantly. Your bunk was damp. Your clothes were damp. Your shoes rotted from perpetual moisture. You ate standing up because the mess had 8 seats for 44 men. The food was adequate. Canned goods, some frozen meat, plenty of coffee, but monotonous after months. The worst part was the cold. The ship had steam heat that worked intermittently. When it failed, the inside temperature matched the outside. We slept in multiple layers and still shivered. The only warm place was the engine room, and you couldn't stay there." These conditions weren't accidental. They reflected deliberate design priorities. Kaiser built ships to carry cargo, not to provide crew comfort. Every ton devoted to nicer quarters meant 1 less ton of cargo delivered to the war. Every dollar spent on amenities meant fewer ships built. The merchant seamen suffered so that soldiers could eat, tanks could reach the front, ammunition could reach the guns. Nobody pretended this was fair or pleasant. It was simply necessary. The naval armed guard aboard liberty ships faced even worse conditions. These Navy personnel, 20 sailors and 1 officer, manned the defensive weapons, 1 3-inch gun aft, 1 5-inch gun forward, 8 20mm anti-aircraft guns. Their quarters consisted of whatever spaces remained after the merchant crew berthed. Often this meant sleeping in the gun tubs or rigging hammocks in passageways. They trained constantly, but rarely engaged enemy aircraft or submarines. Their primary function was deterrent. U-boats avoided surfacing near armed vessels because 1 lucky hit could sink a submarine. The psychological burden of maintaining vigilance voyage after voyage, knowing 1 moment's inattention might doom the ship, ground down these young sailors. Many suffered what would later be recognized as combat stress, despite never firing their weapons in anger. Despite these harsh realities, liberty ships accomplished their mission. Between 1942 and 1945, they carried 75% of all cargo shipped from America to overseas theaters. The 2,710 liberty ships delivered 185 million tons of material: food, fuel, ammunition, vehicles, aircraft, everything required for industrial-scale warfare. They sustained Britain through blockade, supplied Russia through Arctic convoys, provisioned Pacific Island campaigns, enabled the Normandy invasion, and maintained pressure on every front. The strategic impact dwarfs individual ship experiences. Kaiser himself never served aboard a liberty ship. He never experienced the cramped quarters, the constant dampness, the danger from U-boats. His connection to these vessels remained abstract: production numbers, delivery schedules, cost metrics. Critics consider this disconnect damning. The man who created these miserable conditions never faced them personally. Defenders note that no general fights in every foxhole. Strategic leadership operates at system level. Kaiser's job was maximizing production to win the war. Improving crew comfort was someone else's responsibility. The efficiency obsession extended beyond ship construction into workforce management that modern observers find troubling. Kaiser's Richmond yards operated on 3 8-hour shifts, 7 days weekly, indefinitely. No weekends, no holidays, no breaks in production. Workers who wanted time off were replaced. The assumption that winning the war justified any sacrifice permitted labor practices that peacetime would consider exploitative. Fatal accidents occurred with grim regularity. Between 1942 and 1945, Kaiser's 7 yards recorded 87 worker deaths from falls, crushing injuries, burns, electrocution, and other industrial accidents. This represents 0.000087 deaths per worker annually, 87 deaths over 4 years across yards, averaging 100,000 total workers. Contemporary construction sites averaged 0.000126 deaths per worker annually. Kaiser's yards were statistically safer than normal construction, despite working at emergency pace. But 87 families lost fathers and sons to build these ships. The deaths weren't negligent. Investigations showed proper safety equipment and procedures. They were simply inevitable when 100,000 people work with heavy machinery around the clock for years. Kaiser's response to worker deaths demonstrates his systematic philosophy. After every fatal accident, investigators determined root cause and implemented procedural changes. Fall from crane boom led to mandatory safety harnesses and training modifications. Welder burned in enclosed space led to ventilation requirements and gas monitoring equipment. Each death generated specific prevention measures rather than vague safety exhortations. The statistical decline in accident rates over time showed the system working, but couldn't resurrect the early casualties who died before procedures improved. Labor relations also reveal uncomfortable aspects of emergency production. Kaiser actively recruited African American workers from the South, promising fair wages and non-discriminatory hiring. The Richmond yards employed more black workers than any American shipyard had ever attempted, eventually reaching 14,000 African American employees, 15% of the workforce. This seems progressive until examining the details. Black workers received equal pay, but faced systematic segregation. Separate dormitories, separate cafeterias, separate recreation facilities. African Americans could work beside white workers, but couldn't eat with them or live with them. Promotional opportunities heavily favored white workers. Qualified black employees remained in lower positions while less experienced white workers advanced. When black workers protested these conditions, Kaiser's management responded with incremental adjustments rather than fundamental policy changes. The yards needed the labor more than they wanted justice. Kaiser himself, when questioned about segregation policies, stated, "We hire anyone willing to work and pay them equally for equal work. How they choose to socialize off the clock is their business." This response reflects the era's limited civil rights consciousness, but also reveals Kaiser's fundamental pragmatism. He cared about production metrics. Social justice wasn't his mission. He would hire anyone, work them as hard as possible, pay them fairly, and ignore everything beyond productivity. Some historians view this as progressive for 1942. Others see it as exploitation wrapped in equality rhetoric. The women Kaiser hired faced similar complexities. 27,000 women worked in Richmond yards: welders, crane operators, mechanics, electricians, every role except top management. Recruiting posters celebrated Wendy the welder, Kaiser's answer to Rosie the riveter. Women received equal pay for equal work, revolutionary for the era, but they faced constant harassment, inadequate sanitary facilities, the yards had been designed for male workers, and systematic assumption they would leave when the war ended, which is exactly what happened. When Japan surrendered, Kaiser began layoffs within weeks. Women and minorities went first, replaced by returning white male veterans who received preferential rehiring under federal law. The women who had built hundreds of ships suddenly found themselves unemployed. Kaiser's revolutionary employment policies evaporated the moment they weren't strategically necessary. The yards returned to traditional hiring patterns, white men doing skilled work, minorities and women in support roles if employed at all. These uncomfortable realities don't negate the achievement, but add necessary context. Kaiser revolutionized industrial production by treating workers as interchangeable components in an optimized system. This approach won the war, but reduced human beings to labor units measured by output rates. The same systematic thinking that eliminated construction inefficiencies also eliminated concern for anything beyond productivity. Whether this represents acceptable wartime pragmatism or indefensible dehumanization remains debated. What's undebatable is the strategic impact. By mid-1944, American merchant tonnage exceeds losses by 3-to-1 ratio. The Atlantic becomes American highway rather than German killing ground. Convoys arrive regularly in Britain, Russia, and Mediterranean ports. The supply situation reverses completely. Now German forces starve while Allied armies overflow with equipment. The logistics revolution Kaiser enabled allows strategic options that 1941 planners considered impossible. The Normandy invasion exemplifies this transformed reality. Operation Overlord requires transporting 156,000 troops and 20,000 vehicles across the English Channel on D-Day, then sustaining them with 600 tons of supplies daily per division. This demand exceeds the entire British merchant fleet's capacity. Liberty ships solve the problem. In preparation for D-Day, Liberty ships transport 2.5 million tons of supplies from America to Britain. After D-Day, they maintain supply flow across the Atlantic while smaller vessels shuttle material from British ports to Normandy beaches. The Red Ball Express, the famous truck convoy system that sustained Allied armies racing across France, entirely depended on Liberty ships. The 6,000 trucks required 300,000 gallons of gasoline daily. That fuel arrived in Liberty ships from Texas refineries. The ammunition those armies fired, 12,000 tons daily at peak operations, arrived in Liberty ships from American factories. The replacement vehicles, the spare parts, the medical supplies, the rations, all traveled aboard Liberty ships that didn't exist 3 years earlier. Soviet survival similarly depended on Kaiser's production. Between 1941 and 1945, Allied convoys deliver 17.5 million tons of supplies to Russia via Arctic routes and Persian Gulf ports. This material includes 12,000 tanks, 11,000 aircraft, 400,000 trucks, 35,000 motorcycles, and countless ammunition, food, and raw materials. The merchant ships carrying these supplies, braving Arctic storms, German U-boats, and Luftwaffe attacks, are predominantly Liberty ships. The Eastern Front, where Russian armies destroy German divisions, is sustained by cargo vessels built in California by housewives and farmers who learned welding in 2 weeks. Kaiser's contribution extends beyond Liberty ships into other emergency production programs. His yards build 50 escort carriers, small aircraft carriers converted from merchant hulls for anti-submarine patrol. They build LSTs, landing ship, tank, for amphibious operations. They build tankers, troop transports, repair ships. The same modular construction methods, systematic training, and parallel production processes that revolutionize cargo ship production apply to every vessel type. Kaiser Industries delivers 1,490 ships total across all types, more tonnage than any private shipbuilder in history. The cost analysis reveals both triumph and tragedy. Building Liberty ships using traditional methods would have required approximately $26 billion, $1943, equivalent to $420 billion in 2024. Kaiser's methods reduced this to $12 billion, a $14 billion savings, enough to fund the entire Manhattan Project 11 times over. But this figure ignores human costs. Those 87 workers killed in yard accidents, the crews who died aboard ships that broke apart from structural failures, the African-American workers who faced segregation despite equal wages, the women discarded when no longer needed. Cost-benefit analysis struggles with inputs measured in different currencies. By war's end in August 1945, Kaiser's empire encompasses 7 shipyards, 3 steel mills, multiple cement plants, and magnesium production facilities. He employs 200,000 workers and delivers more war material than some Allied nations produced entirely. His personal wealth increases from $3 million in 1940 to an estimated $300 million by 1945, a 100-fold increase in 5 years. He achieves this through aggressive bidding on cost-plus contracts that guarantee profit regardless of expense overruns. Traditional shipbuilders receive fixed-price contracts that transfer risk to the builder. Kaiser negotiates cost-plus fixed-fee contracts where the government pays all costs plus guaranteed profit. When construction takes longer or costs more than estimated, Kaiser's profit doesn't decrease. Critics call this war profiteering. Defenders note that without these guaranteed profits, Kaiser would never have risked the capital to build 7 shipyards from nothing. The fundamental question persists. Did Kaiser save or exploit the situation? Did he serve his country or primarily serve himself? The answer contains uncomfortable both and rather than clean either or. He delivered ships America desperately needed using methods nobody else imagined. He also enriched himself enormously through government contracts while workers died in his yards. These facts coexist without negating each other. Admiral Land, who initially dismissed Kaiser as an absurd civilian meddling in sacred maritime tradition, delivered the most balanced assessment in his post-war memoir. Kaiser was neither genius nor charlatan, neither savior nor profiteer. He was a systematic optimizer who recognized that emergency demands emergency response. Traditional shipbuilding represented peacetime thinking applied to wartime problems. Kaiser simply removed the peacetime assumptions. Whether we should celebrate or condemn the results depends on whether we value victory more than tradition. I valued victory. Therefore, I celebrate Kaiser. But I understand those who remain uncomfortable with his methods. The post-war period reveals Kaiser's limitations as clearly as the war revealed his strengths. Peace removed the emergency justification for his methods. Merchant shipping returned to peacetime economics where crew comfort mattered, where lowest cost no longer dominated all decisions, where rushing production wasn't virtuous. Kaiser tried converting wartime methods to peacetime success, building automobiles using modular construction, prefabricated housing using shipyard techniques, applying systematic optimization to consumer goods. These ventures largely failed. The Kaiser automobile, despite advanced engineering, couldn't compete with established manufacturers. The prefabricated housing market proved too fragmented for systematic mass production. The post-war economy wanted customization and quality, not minimalist efficiency. Kaiser's systematic approach, which overwhelmed German U-boats, couldn't overcome American consumer preferences. He remained wealthy and influential, but never replicated his wartime impact. By his death in 1967, he was remembered primarily for Liberty ships, that brief period when emergency aligned perfectly with his particular genius. The Liberty ships themselves mostly disappeared quickly. Designed for 5-year service life, they exceeded expectations by lasting through the war. But peacetime exposed their limitations. Slow speed made them uncompetitive. Modern cargo vessels achieved 15 to 18 knots versus Liberty ships 11. High fuel consumption made them expensive to operate. Minimal crew comfort made them unpopular with peacetime maritime unions. By 1950, most Liberty ships sat in reserve fleets. the famous mothball fleets photographed in rows across bays and rivers. Some sold to foreign operators. Some scrapped for metal. A few converted to specialized uses. Today, 2 operational Liberty ships remain: SS Jeremiah O'Brien in San Francisco and SS John W. Brown in Baltimore, preserved as museums. The final assessment must acknowledge paradox. Kaiser's revolution in shipbuilding produced vessels that were slow, inefficient, uncomfortable, and short-lived. Yet they were exactly right for their moment. They were built fast enough, carried enough cargo, survived long enough to win the war. Strategic success doesn't require optimal solutions. It requires adequate solutions delivered when needed in sufficient quantities. Kaiser understood this perfectly. Admirals wanted elegant ships that reflected centuries of maritime tradition. Kaiser built adequate ships that reflected industrial reality. The deeper lesson extends beyond shipbuilding into industrial warfare generally. World War II was decided not by generals making brilliant tactical decisions, but by engineers making systematic production decisions. The side that built more trucks won battles of maneuver. The side that produced more ammunition won battles of attrition. The side that delivered more supplies sustained operations longer. Victory came through logistics and production capacity more than combat brilliance. Kaiser's contribution was recognizing this reality before military traditionalists and acting on it systematically. He didn't invent welding or prefabrication or modular construction. These techniques existed. He recognized that emergency warfare demands emergency methods, that tradition becomes liability when speed matters more than perfection, that ordinary people using systematic processes can outproduce experts using traditional methods. These insights seem obvious in retrospect, but were revolutionary in 1941. The workers who built these ships, farmers, housewives, displaced laborers, anyone willing to learn, remain the story's forgotten heroes. The narratives celebrate Kaiser's vision, but 200,000 anonymous workers executed that vision through exhausting shifts, dangerous conditions, and modest wages. They learned skills in weeks that traditionally required years. They built ships faster than anyone thought possible. They sustained this effort for 4 years, despite knowing they'd be discarded when no longer needed. Mary Thompson, who welded hull plates at Richmond Yard No. 2 from 1942 to 1945, reflected in a 1982 interview. "People ask if I'm proud of what we did. Proud isn't the right word. We did what needed doing. Nobody asked if we wanted to work those hours or learn those skills or build those ships. The war needed ships, so we built ships. Simple as that. I'm not proud. I just showed up and did my job, same as 90,000 other people at that yard. Kaiser got famous. We got forgotten. That seems about right. We weren't there for fame. We were there because the alternative was losing everything." That pragmatic acceptance, showing up, doing difficult work well, expecting no recognition, represents the real triumph of Kaiser's shipyards. He created a system that transformed ordinary people into extraordinary producers, not through inspiration, but through systematic optimization. The assembly line principles that Henry Ford applied to automobiles, Kaiser applied to ocean-going vessels. The human cost of this transformation, workers reduced to interchangeable parts, traditional craftsmanship replaced by repetitive tasks, individual creativity subordinated to systematic compliance, purchased victory at a price that peacetime wouldn't accept. But wartime did accept it. For 4 years, American industrial capacity overwhelmed Axis production through systematic application of these principles. Liberty ships represent just the most visible example. The same systematic thinking produced 300,000 aircraft, 86,000 tanks, 2.4 million trucks, 41 billion rounds of ammunition, and endless additional materiel. This production avalanche buried German and Japanese forces under quantitative superiority that no amount of tactical brilliance could overcome. Admiral Dönitz, when asked after the war what could have changed the Atlantic battle's outcome, responded, nothing. Once American industry mobilized fully, we were mathematically defeated. Our submarine force sank ships impressively, but they were attempting to empty an ocean with buckets, while America filled it with rivers. The strategic impossibility became obvious by 1943. We continued fighting because admirals don't admit defeat, but the mathematics were conclusive. That mathematical conclusion, industrial capacity defeating tactical excellence, represents Kaiser's true legacy. The 4-day ship was theatrical demonstration. The real revolution was systematic transformation of shipbuilding from craft to industry, from art to engineering, from individual expertise to systematic processes. This transformation made admirals cry, not because it was wrong, but because it proved their entire worldview obsolete. 3,000 years of maritime tradition taught that ships required master craftsmen, extended construction periods, careful attention to detail, respect for the sea's demands. Kaiser demonstrated that ships require systematic processes, parallel construction, adequate quality rather than perfection, and respect for deadlines over tradition. Both approaches work in their appropriate contexts, but when nations fight industrial wars, the systematic approach wins because scale overwhelms excellence. The man who never built a ship destroyed 3,000 years of shipbuilding tradition, not through innovation, but through optimization, not by creating something new, but by removing everything unnecessary, not by making ships better, but by making them faster. Whether this represents progress or tragedy depends entirely on what you value: tradition or victory, craftsmanship or efficiency, individual excellence or systematic adequacy. Kaiser chose victory, efficiency, and adequacy. History, written by winners, validated those choices. The admirals who wept over welded ships and modular construction retired into irrelevance, their expertise made obsolete by farmers wielding welding torches. The tradition they defended couldn't defend the nations that needed defending. In the end, 4 days and 15 hours proved sufficient to change naval warfare forever. Not because the ship built in that time was exceptional, but because it was adequate and replicable. When adequacy scales infinitely and excellence scales slowly, adequacy wins. That lesson, learned in Kaiser's Richmond shipyards between 1941 and 1945, remains relevant wherever tradition confronts emergency, wherever craftsmanship meets deadline, wherever the perfect becomes enemy of the sufficient. The Liberty ships are gone now, scrapped or rotting in forgotten harbours. The admirals who opposed them are dead. The workers who built them are dying. But the principle remains. When survival demands it, systematic adequacy overwhelms traditional excellence. Kaiser proved this at scale, made admirals cry over its implications, and changed industrial warfare forever. All by refusing to accept that things must be done the way they've always been done. Sometimes the most revolutionary act is simply asking, why not faster?